doing and sometimes enjoying their math homework. If that wasn't enough, multiple students report that our speaker's voice regularly helps them fall asleep. We are delighted to welcome Grant Sanderson, the creator of the legendary YouTube channel 3blue1brown, with over 40 hours of insightful math explainers ranging from fractals to machine learning to the best opener in Wordle.
While majoring in math and CS at Stanford in 2015, Grant developed Manum, an open source Python library for creating intricate math animations. The first 3blue1brown videos emerged as a test drive with Manum, but soon the channel took over the world with its stunning visualizations. Today, Grant's videos have been translated into 15 languages, while educators worldwide are using Manum to craft their own explainers. Besides filming YouTube videos, Grant has worked for Khan Academy, designed and taught an MIT course, and even contributed a Netflix documentary about infinity.
In recent years, he started the Summer of Math Exposition, an annual contest of math explainers that has encouraged numerous math enjoyers, including myself, to try their hand at teaching math online. Whether Grant has saved your grade, sparked your love for math, or helped you fall asleep, please invite him to the stage with a roaring round of applause.
Daria is too modest to say that she was one of the winners of that contest that she referenced there, so just want to put it there. I will do my best not to put you to sleep, which was a risk I wasn't aware of until 30 seconds ago. I want to talk to you today about topology, but I'm not assuming anyone knows any topology. Usually, among students of your age, that would just be an obvious assumption, but I'm led to understand there's actually a topology class in this school. And out of curiosity, just raise of hands, how many people just know what topology is? Like that brings something to mind. And then how many people aren't sure what topology is? Definitely no judgment. Great. So no assumptions here. When I was a student, around your age, I was a math nerd. This probably comes as no surprise. And I would go to certain events targeted at inspiring the youth about math. And I remember facts from topology would come up as certain examples. And a common thing someone might do is they would have us play a game with some construction paper, where they might say, make a long ribbon, and then twist that ribbon, and then paint, tape one of the edges to the other when you do this twist. And they would have us ask certain questions about this shape, like how many edges does it have? If you color, one side of it, what happens? Oh, you realize there's just one side. And it was neat, but I do remember kind of thinking, for sure, how is this math? Like, how does this actually help you solve problems? And they would come up with other examples. They would say, like, to a topologist, if you look at a coffee mug or something like this pitcher, it's got a single hole in it. And that makes it equivalent to a topologist to, a donut or a bagel, because that also has one hole, whereas, a cup or many other shapes would be equivalent to a sphere, because they don't have a hole. And I'd have that same thought. I'd be like, for sure, cool. How is that math? Like, how does that actually help you solve problems? And it wasn't until I came across the thing I want to share with you today that it actually sunk for me, that somehow studying the nature of these strange shapes in a way that doesn't depend on how close each point is together, but in some sort of looser sense of what the structure is, you might actually be able to solve a problem. Now that sounds very abstract, but I want to show you what I mean. So there's a certain question that's called the inscribed square problem that goes as follows. If you're going to squiggle some sort of line through space, you just imagine you're doodling and you draw some line. If it's a closed loop, so you end where you started, you've got this closed loop, is it always the case that you can find 4 points somewhere on that loop that make a square? So for the one on screen, I can find 4 points here, and those 4 points happen to form a square. Now the question is, can you always do this? No matter what loop you draw, is it going to be possible to draw a square? So you could either come up with a counterexample where no square exists, or you could somehow prove that for every single one there is a square. This is unsolved. No one knows the answer. You would become very famous if you could answer this question. It's solved in partial cases. So for example, some very smart people found if it's a smooth curve, basically most of the curves that you can actually draw with a pencil, it's solvable. But the trickiness comes with a lot of these esoteric shapes in math, like fractals, where it might not necessarily be smooth. But the only constraint is that it's continuous, which would mean that in principle you could trace it out with a pencil without ever having to lift that pencil up. So this is unsolved. But if we relax the question a little bit, we can get a problem that's still very hard to solve, but you and I can actually go through the process of answering it today. And the answer is just amazing. So you could maybe, with the inscribed square, think about very simple symmetric situations. It gets challenging if you have some less symmetric situation. Even thinking about how you could write an algorithm that would, brute force search for something that's close to a square is a little bit tricky. But if we relax it to rectangles, and we instead say, can you always find a rectangle? There's a clever thing you can do. So the way this is going to start, instead of saying, can I find 4 points that make the rectangle, I'm going to slightly tweak the framing of the question and say, can you find 2 different pairs of points, so that if you look at the midpoint of one of those pairs, and then the midpoint of the other, those midpoints line up. And then each pair has the same distance apart. So it's a slightly different framing, but if you think for a moment, if I just abstractly describe 2 pairs of points somewhere sitting out in space, but they're constrained so that they have to have the same midpoint, and then the distance between each one of those pairs, so in this case the distance from A to C and the distance from B to D are both the same. Kind of hold this in your mind, you could maybe convince yourself those have to form a rectangle. A fun little exercise, if you're into practicing mathematical proofs, is to turn that into a more rigorous proof. Why is it necessarily the case that sharing a midpoint and sharing the distance makes these a rectangle? But when you do this, what it means is what we're looking for any kind of closed loop is a kind of coincidence, where if you search through all the different possible pairs of points, you want to find this alignment, where they have the same midpoint, same distance apart. And the spirit of topology, and the spirit of a lot of math, is to sometimes encode state like this. In this case, for a pair of points, you've got the midpoint, you've got the distance apart. You want to somehow describe that as a single point in some sort of higher space. Here's an example of what I mean by that. So if we take this loop and we situate it in 3D space, and we imagine it sitting somewhere on the xy plane, if I want to somehow communicate what's the midpoint and what's the distance apart with a single point in that space, here's one thing I could do. I say, all right, let's take some pair of points, arbitrary pair of points somewhere on that loop. Consider the midpoint, which is also somewhere on the xy plane. That's going to describe for us like an xy coordinate. The only other piece of data I want to encode is their distance apart. I'm going to make that distance apart a z coordinate. So you might imagine taking a line that describes that distance and moving it up. This is a way of mapping pairs of points into 3D space. And what we want is to see if there's 2 different pairs that land on the same point when you do this mapping. Now, when I was making a video about this a while back, I knew the argument, and I knew it in the abstract, but I had no idea what this would actually look like, because math is often described in this sort of abstract way. And so it's very fun to go in and actually instruct the computer to display what comes up if for every possible pair of points, we make this mapping. We associate it with a certain 3D point. And for this curve, this is what you end up getting. It looks sort of like a Frank Gehry architectural design, one of these fancy opera houses. But it has a meaning. It has this nice representation where every one of these points on the surface encodes the information we care about for an unordered pair of points. And so proving the inscribed rectangle problem, in a manner of speaking, comes down to asking, does this surface ever intersect with itself? In the sense that you have 2 different pairs of points that land on the same output here. And we want somehow to have an argument that's really flexible, that's not dependent on the particular loop. Because if you change what that underlying loop is, it changes the surface that we're describing up above. And so you can kind of mix this around, various different loops that you have. You've got these very, very beautiful different surfaces that might come up above. And we want to somehow describe the sense in which this has to intersect itself, that there has to be some kind of crossover. And you might think, okay, this is it's like an interesting visual that you can do, but how does this actually help you solve it? How is it actually leading you towards an answer? Because at the end of the day, you're still asking the same question. You're just saying, when is it that you have 2 distinct pairs of points that have the same midpoint and have the same distance apart? And so at this point, tiny little sidebar, anytime you're telling a story, I think it's very important that you plant certain seeds along the way that can maybe sprout up a little bit later. And this can be something important for fiction to make the fiction more enjoyable. It's also important for math lessons. So the author Chekhov had this description of if in Act 1 there's a gun hanging on the wall, then at some point in Act 2 or 3 that gun had better be fired. And I think the same kind of applies in math lessons, where every now and then If you've mentioned something early on, you've got to make sure that you loop back to it later. And if anything, it's kind of helpful to make sure you hang up a gun on the wall a little bit early so that the seeds are planted. And in this case, the gun I want to hang on the wall is to have you think about all of the points where the pair looks like x comma x. Meaning the pair of points that we're thinking about is really just the same point listed twice. And I'm going to ask, where does that end up in this three-dimensional picture? Where do all of those pairs of points that are really just x comma x land? If you think about it for a moment, if you have 2 points that are approaching each other, then the midpoint, it's really just going to be the same as the points that were listed, because the midpoint between the point and itself is just that same point. The distance is 0, so that z-coordinate is 0. So all of these ones, this kind of special pairs of points that's really the same thing listed twice, those end up on the curve itself. Might not be clear how that's relevant, just want to hang that up on the wall, maybe that gun will go off later. But right now we're trying to think, is there another way that we could understand pairs of points in a geometric way? And if we just had a description of single points, one thing that we could start to do is associate each point on the curve with a number. And so you might imagine basically walking around the curve and numbering all of the points, let's say from 0 up to 1 in some continuous way, which in a geometric manner of speaking is associating all of the different points on the curve with an interval, the interval between 0 and 1. But when you do this, if you're thinking of the relevant geometry, associating it with the interval loses some of the information. It loses the information that it's connected. So you have to somehow remember or make a note to yourself that you snipped the curve. Wherever you started it at 0 to go around to 1, if you consider that a mapping to the interval, effectively you need to think of the numbers 1 and 0 as glued together. And if you remember in the back of your mind that 1 and 0 really represent the same point, that's a way of preserving the fact that this is a closed curve. You might ask, okay, well, what does that matter for us? This becomes a little bit more interesting once we start talking about pairs of points. Because if we want to talk about pairs of points, and we've somehow associated all the different points around this curve with numbers, between 0 and 1, let's say, then a pair of points would look like a pair of numbers, and we could basically come up with a coordinate plot. We could have a unit interval represent an x-coordinate, and then a separate unit interval represent a y-coordinate. And then for any given pair of points here, you just draw x comma y, and you've associated each pair of points with something inside this unit square. But on its own, that would have lost the information that this came from a closed loop. And so if you want to remember the fact that it came from a closed loop, you have to remember that everything with an x-coordinate of 0 really needs to be glued to everything that was an x-coordinate of 1. And similarly, everything that's a y-coordinate of 0 has to be glued to everything that's a y-coordinate of 1. And so the way I have it represented here, all of the blue arrows on the bottom, that represents everything where the y-coordinate is 0. And I give a sense of a direction to it so we know which way that we're going to glue this. And everything up top, that's all the y-coordinates all the points where the y-coordinate is 1. So you want to imagine in your mind gluing those blue arrows on top of each other. And at the same time, everything on the left, all those pink arrows, that's where the x-coordinate is 0. Everything on the right, that's where the y-coordinate is 0. So you want to glue those together. So, question, anyone, if we were to make those two gluings and then describe this as some kind of shape, what shape would we get? Feel free to raise hands, toss it up. Donut, yeah, great, it's a donut. This is where donuts come from. To a mathematician, at least. It comes from taking a unit interval and then gluing the two different sides in the appropriate way. Now, what I want to emphasize, though, it's not just that we're saying, like, hey, let's talk about donuts because they have holes in them. The reason that this came up is it's a very natural way to describe the idea of pairs of points on a loop. And so in some sense, statements about pairs of points are equivalent to statements about donuts. And equivalent in the sense that you could change what the specific loop is, you could modify it a little bit, but as long as it's a closed loop, the thing that encodes the fact that it was a closed loop when you're instead thinking about pairs of points is this donut structure, because of that gluing that we did. But this is not quite right for the question that we have. This isn't exactly the surface that we want to think about. Because if we go back and we think about a given pair of points, let's say the one that was described by the coordinate 0.2 and the one that's described by the coordinate 0.3, that would be considered, in our scheme right now, distinct from if you swapped them. If I instead said 0.3, 0.2, those are different points inside this square of ours. And at the end, what we want to do is somehow make a statement that says, two distinct pairs of points map to the same thing in this strange Sydney Opera House looking structure. And if you think about what we're going to do here, if I claimed to you that I've proven that two distinct pairs of points, have the same midpoint and the same distance apart, but we counted AB as being a different pair from swapping it around and being BA, well, there you have an example of two distinct pairs of points with the same midpoint, same distance apart. But it's not really what we're looking for, because that's a little bit like saying, sure, there's always a rectangle in these curves, as long as we consider the infinitely thin rectangle that just has one side length of 0 and another side length that's, non-zero. So what we really want to do is make another gluing here, where every point that looks like x comma y, we want to somehow glue that to the points y comma x. So in our picture, does anyone want to throw out what that means for how we're going to somehow modify this to do the gluing that we want? To say every point that looks like x comma y, I want to glue that to the point that looks like y comma x so that we are uniquely describing unordered pairs of points. Any ideas?
Fold it diagonally.
Fold it diagonally, great. Grilled cheese style. So if you think about it, any point x, y, when you swap the coordinates, you can think of as reflected across the diagonal line that goes from the point 0, 0 up to the point 0, 1. So we take that diagonal line and we fold it, and that's great. It means all of the points from one ordering of the pair get glued to the other. But it makes the arrows a little bit tricky, because I'm keeping those arrows so that we know the orientation that we have to do. It's going to make that a little bit strange to glue together. Before we do that, though, I just want your eyes to turn back to the gun that's hanging on the wall and think about all of the points x comma x. Where do they end up in the current diagram that we have? So right now, all of the pairs of points that are really the same thing listed twice exist on the crease of that fold. So the crease of that fold represents these points x comma x. Just a thing to keep in mind, just something to have there in the back of your mind. The more pertinent question for us, though, is how do we actually glue these arrows together? Because it's super weird at this point, actually, if you think about it. Because, I'm going to go over away from the mic to just reference it. You want the point that's like on the lower left here to be the same as the one that's on the lower right. And then this point here to be the same that's on the top. And if you just play around that, it might feel like a kind of impossible thing to do in your mind. But there's a very fun trick that you can do with these sorts of topological gluing games, where sometimes you need to take a step backwards before you take a step forward. So the awkwardness with this picture is that the very lower right point feels almost like a contradiction, because it somehow needs to get glued both to the bottom left and also to the top right. So what I'm going to do is cut this up a little bit to make the purple arrows easier to glue together, and I just need to remember what cut I made. So I'm going to cut this along another diagonal, and I'm going to represent that with some yellow arrows. So I cut it, I take them apart, but I just need to remember to glue those yellow arrows together again. Once I do that, I can glue the purple arrows together. And I glue those purple arrows together, it's not going to be a problem. I'm going to get something that looks like a square. I just need to remember to glue those yellow arrows together again. Now, anyone want to shout out, what do we get if we glue the yellow arrows together again? Mobius strip! This is what a Mobius strip is. It's not just a random shape to play around with in like a construction paper class. It represents something. So in this case, the thing that it's representing, it's kind of the most honest mathematical description of unordered pairs of points on a loop. Now that might sound like a kind of weird thing, who would care about representing unordered pairs of points on a loop? But one, if you're a little bit nerdy like me, that's just cool. It's just a cool thing to think about. But two, for our problem of understanding inscribed rectangles, which might be a stepping stone to solving an unsolved problem, which is the inscribed square problem, this actually gives us a language that we can speak. Because what we're saying is for any closed loop, there's a kind of equivalence between unordered pairs of points on that loop and individual points on a Mobius strip. And again, drawing your eyes to the gun on the wall, the points here that represent all of the pairs of points that are really the same, x comma x, it's that red edge of the Mobius strip. Because if we kind of trace back a little bit here and we think what happened to the crease of that fold, I'm drawing that crease in red. We do our little cutting game, we cut it with the yellow, we do some of the gluing, we put it together. If you consider what happens to that edge, which I'm still coloring in red, after all of the gluing, it ends up as this single edge of the Mobius strip. And so now if you think back to the surface that I had earlier, which was a geometric representation for all possible pairs of points, and more importantly, the bits of information we cared about, where's their midpoint and how far apart are they? What we have here is a mapping from the pairs of points on the loop to that. We also have this equivalence between individual points on the Mobius strip and pairs of points on that loop. So what we're really describing is a mapping from the Mobius strip onto this sort of three-dimensional Sydney Opera House looking structure. And the thing that you want to prove, or the claim that you want to make, is that this mapping has an intersection, that there's two distinct inputs that end up on the same output. And as just a reminder for why, if that was the case, for that mapping from the Mobius strip to this surface to have two inputs that land on the same output, that's the same thing as saying there's two distinct pairs of points with the same midpoint, same distance apart. That's going to be the same thing as enforcing that the 4 points represented there make up a rectangle. Again, this is one of those things where I had read an abstract argument about this. I had no idea what it would look like. Like, what does this mapping actually look like? And took no shortage of delight in just asking the computer to map it out. So in this case, if you do the actual mapping, you make this association between individual points on the Mobius strip and the sort of Sydney Opera House, when you have inputs move over to their outputs, this is what it looks like, which was amazing to me. It's so fun. And you'll notice, actually, the important part here is what happens to the red edge of that Mobius strip. So if I kind of go back to the start of it, notice how the points on that boundary of the Mobius strip, the red edge, end up glued on this xy plane, on that loop. And the pertinent part here is that we want to somehow claim that this can't be a one-to-one mapping. It can't be something where individual inputs all go to unique outputs. And that we have this collision that we want. And if you play around in your mind, you might be able to at least believe that this is a very plausible fact. Because if you picture a Mobius strip in your mind, and kind of tweaking it around, maybe it's made out of putty, and trying to somehow make it such that that edge that has a twist, is constrained to be on a 2D plane, in this case the xy plane, while everything else from the strip is above, you can pretty quickly convince yourself that this really doesn't feel like it should be possible. Now, actually rigorously proving this is impossible takes a little bit of extra work, but I think this is something that actually motivates why topologists will come up with certain definitions that they do. Because you have this visceral feeling in your heart right now that, okay, this feels impossible. It feels like there's no way to take a strip, a Mobius strip, map it into 3 dimensions in such a way that its boundary gets constrained to the xy plane and the rest of it is up top. It's true that that's impossible, but in order to do that, you need to build up a little bit of machinery. So some of the topics that you might come across if you were to take a topology class, whether here or whether in a university or whether just studying it for fun later in life, there would be descriptions of things like non-orientable surfaces or winding numbers and such. And one of the motivations for having these things is to take this vague intuition of a certain impossibility like this and turning it into something rigorous. But at least at this point, at least if you believe me that this is impossible, that does prove the inscribed rectangle problem. And what's very fun about this, actually, I made a video describing some of this stuff many, many years ago. And since that time, there was actually a further development in the research here. So in 2020, during the pandemic, there was a pair of researchers who got together over Zoom, wanted something to do during the time when they were at home, and thought they would tackle a variant of this problem. And so they had, what was known at that time is that for smooth curves, you can solve the inscribed square problem. It's only the really jaggedy fractal ones that end up giving you an issue. But one of the other unsolved questions was, okay, even if you can find a rectangle, can you necessarily find rectangles with all possible aspect ratios? So a square would be something with aspect ratio 1 to 1, as in the ratio of the side length, one side length to the other is 1 to 1. Other aspect ratios that come up in film would be like 16 to 9 or 2 by 1. And it was thought that maybe it's the case you can always find rectangles of any aspect ratio. They ended up proving this in 2020, and the method that they used is not that different from what we're playing with here. It actually also had to do with describing mappings of a Mobius strip. In that case, it wasn't into 3-dimensional space, because if you care about the aspect ratio, if you think about these pairs of points, you also care about the angle between them. And that angle between them gives you another parameter that's being described. So instead of mapping into a 3-dimensional space that encodes the xy coordinates for the midpoint and the distance apart, it actually involves mapping into a 4-dimensional space, where that 4th dimension is going to encapsulate this extra angle. And so if you look at their research, it starts off by describing constraints about mappings from Mobius strips into 4 dimensions. And it's so easy, as an outsider looking in, who's not necessarily into math, to think that that's just kind of nonsense, and that's a strange thing to be studying. Like, why would a researcher care about mappings from a Mobius strip into 4 dimensions? But at least if you've gone through this, you can start to see why it's not about 4 dimensions being an aspect of physical reality in some way. It's actually just a matter of it encoding certain state that we want. And a lot of different facts in math end up looking like this. And a lot of the studies around higher dimensional geometry are relevant because of this. When someone makes a claim about a lattice in 24 dimensions and things like this, it's not necessarily only useful if the universe somehow had 24 dimensions. It's useful for anything where you might have 24 different parameters and somehow you need to describe the essence of what's going on with that construct. So in this case, I can chat later if anyone wants about approaches that you could take to make this more rigorous, the idea that putting a Mobius strip into 3 dimensions such that its boundaries on the XY plane is impossible. A little bit too much to get into with the time allotted here, but I did want to leave a little bit extra time at the end just in case anyone has questions, either about this or anything else. And then after that, I'll be around through the day, and I think coming to some of your classes later on to chat more about this. But right now, any questions that pop up about some of this stuff? Oh, great, yes?
Really quickly before I begin my question, I'd like to thank you so much for coming today. I know your work has inspired so many of us, and thank you so much. My question to you is that it seems that in schools now, the beauty of mathematics is often underappreciated and is often seen as a chore. What would you say to someone who is underneath that belief?
Okay, so just to repeat the question in case it didn't come through, the claim is that the beauty of math is often lost in classes and viewed as a chore. Honestly, I think there's something to be said for the fact that math done outside of a school environment just feels different to a student than when it's done inside a school environment. Some schools are really great about this. I'm sure this is one of those schools where the classes themselves can feel quite engaging. But realistically, if there is a lot of hard work that's involved in prepping for a particular test, you can work within that confine, but I think the best chance to expose someone to the beauty of it is to have something that's extracurricular. Maybe it's framed as like a problem-solving session. Maybe it's framed as some of these math contest type problems. But once you're in a more relaxed environment where it's not so weighty, like your grade depends on this, I think there's more chance to be playful with it, because sometimes the most fun aspects of math come not from directly beelining towards a solution that you want, but noticing something kind of intriguing and giving yourself the room to ask, like, oh, what happens if I do this, or doodling in that direction. Now, in the confines of a class, I think there's lots of different examples where just trying to put a picture to it in some way can go a long way. So maybe if you're teaching the quadratic formula, this is something you can teach in very different ways. You could memorize it. You could say, here's the formula. Now we will memorize it. You could also try to derive it. You can go through the exercise of completing the square so that it feels a little bit more discovered. But even that, there's a lot of muscles you've got to exercise to go through all of it, and it's not something that's easy to necessarily remember. But there's some very beautiful pictures that you can draw to communicate the spirit of completing the square, where you're literally looking at a square that you need to complete. And I'm a big believer that sometimes having a clear picture like that can let something land in someone's mind a little bit more deeply. So whenever there's a chance, stepping back and asking, what is the single diagram that could somehow capture this? I think that can go a long way for the question that you mentioned here. All right, one more question perhaps, and then.
What have you learned from running 3blue1brown over these years, and how do you think the channel has evolved as a result?
Okay, what have I learned from running 3blue1brown? The early conception of it in my mind, I wasn't really thinking of it like, oh, I want to have a YouTube channel, I want to grow the YouTube channel and have subscribers. It was much more personal than that. I found a lot of joy in trying to visualize math in certain ways. And the original concept was to describe the kind of math that you're unlikely to see in school. So this kind of topic would actually fit right into that. And for students who are already kind of bought into math, I think that can be quite fun to see the things that you wouldn't see in school that it's on those other sides. As time went on, I think I gained a much deeper appreciation for how when you choose a topic that's not necessarily the most original in the sense that there's no other video that's on this topic, but it's a commonly searched thing, like a linear algebra, or what is a Fourier transform, or how do neural networks work, that those actually have the deepest impact on people because it's just meeting students where they are. There's lots of people who struggle with that. And if I'm going to pour so much time into the visuals, rather than catering just for the people who are already math nerds and are already bought into it and taking all the esoteric topics, that it's just much more worth my time to answer the questions that most people have, or people who are in certain classes. It sounds obvious in hindsight, like cover the topics people want to learn. But that just actually was a shift in terms of my relationship with it, where it went from being something that was much more personal to instead being a little bit more centered on addressing what people might want to learn. Again, sounds obvious. I'm embarrassed it took me so long to realize, but it does mean I try to resist the urge to dive into the things that are those esoteric, nerd, snipey topics that catch me. I'll never fully resist. There will always be at least some of those, but it's not necessarily as dominant as it once was. All right, I think that's about the time that I have here. And I have been told, oh God, there's a phrase I'm supposed to use. Seniors, go? Go seniors? Seniors, go.